Good afternoon. It's my great honor and privilege to introduce the next speaker, Professor Goodwin. Professor Goodwin was educated in Australia and worked for a while at Imperial College, London. He has written 9 books in the area of control and estimation. He is a fellow of the Royal Society, London, and he tells me that an exciting aspect of being elected is that you sign the same book as Isaac Newton did. He was recently awarded the American Society of Mechanical Engineers Oldenburger Award, and before arriving in Brazil, he gave the Oldenburger address at Purdue University. He holds 20 patents covering rolling mill automation, mobile telecommunications, and diabetes treatment. Without further delay, I give you Professor Goodwin.
Thank you, Eduardo, for the very nice introduction, and it's wonderful to be here in Brazil and have this opportunity to talk to you. I have no idea of your background. I wish I did, but I don't. So, can I ask that you begin by asking questions? I'll give you some hints when you should ask questions, but I want you to try to interact with me so I can get a feel for where you stand. Maybe you know all this, or maybe you don't. So please work with me. So I'm going to talk about constrained estimation, and in particular I'm going to talk about sparsity issues, and they underpin a lot of problems in estimation and control. This is roughly what I'm going to talk about. I'm going to begin by giving you a very rough overview, and then I'm going to talk about 2 problems in detail. I'm going to talk about regularization, which is becoming a big topic in many areas, including machine learning. And then I'm going to talk about rank-constrained optimization. And these 2 topics are related. I'm then going to do an extra thing that's not written on this slide. I'm going to tell you about an application that I've recently became involved with, which I find very exciting. So that's what we're going to do for the afternoon. Okay, so it's often desirable in real-world problems to restrict the complexity of the solution. And why would you want to restrict the complexity? Well, there are 2 reasons, and I'll come to the second one first. You may, in an optimization, want to minimize the resources that you use in some way. And by restricting the complexity or the class of answers to a problem, you might be able to address this question of minimizing resources. Now, in estimation, there's an even greater reason, and that is to avoid the overfitting problem. Now, what do I mean by overfitting? Well, loosely speaking, you can fit a huge model to anything, but it doesn't mean that you've described the object of interest. So, many of you may work in machine learning, and it's finding application now in many areas: astronomy, protein, molecule analysis, cybersecurity, medicine, finance, and many other areas. But there's always the potential that if you fit a very large model, it will fit the data, it will fit the given data, but it doesn't necessarily mean that it's useful for predicting outside of the given data set. So there's always the risk, if you fit the data beyond prudent limits, that you can simply be fitting erroneous errors, noise, and not really saying anything about the underlying problem. So one topic that some of you might be interested in is that of developing new investment strategies. That sounds like a good idea. There's a lot of work in this, but you've got to be careful that if you back-test investment strategies, so if you have some new strategy and you try it on past data, you can be convinced that this investment strategy is just the way to make a lot of money. But they may fail miserably in practice, because what you've really done is not really understood the finance market, but simply understood other things that were going on in the data set you've got. So my point is, it's easy to fit a given data set, but it's hard to extrapolate from a given data set to say things about the future. Okay. So in this short course, I'm going to concentrate on tools. It's going to be mainly about the tools of restricting the complexity of models. And then in the third part, which wasn't on that slide, I'm going to talk about an unrelated application. Okay, so there's two themes to the talk. One is regularization, and the other is rank-constrained optimization. And I'll tell you as we go along what the difference is. Regularization is a way of sort of limiting the class of models that you fit, but not in a hard way. It's sort of in a soft way. And whereas rank-constrained optimization gives you hard constraints on the complexity of solutions. And I'm going to subdivide each part of this into 4 subsections. I'm going to give you a little bit of motivation, then I'll tell you the tools, and that's the main part of the talk, to introduce you to new tools. And then I'll just quickly go through some applications, and then I'll summarise what we've said. So you can see that there's 2 parts to the presentation, and I'm going to start with regularisation. And we'll begin with motivation. So what's the basic idea of regularisation? It puts a penalty of some sort on the complexity of the solution. Now, let's see if we can take a simple example. What I'm going to do is to use the impulse response of a system. So if you look here, this is the output of a system, this is the input to the system, and this is the impulse response. And you can see we've got a simple convolution linking the input to the output through the impulse response. And I'm going to use the impulse response estimation to tell me something about the frequency response of the system. And the frequency response is just the Fourier transform of the impulse response. All easy. Okay. Right, so how do we set this up as an estimation problem? We're going to just regress the input. So this is a matrix constructed from the present and past inputs, multiplied by the impulse response vector, giving you the convolution of the input with the impulse response, and I'm going to assume some noise. And we know that the least squares estimate for the impulse response is just given by this least squares solution. Okay, so let's assume that the input is white noise and the noise is white noise. And therefore what you can do is very quickly work out what the covariance of the parameter estimates are. Now remember, I'm estimating the impulse response of the channel. If you work in communications, this is the channel impulse response. If you're interested in mechanical vibrations, this is the vibration pattern of the beam or whatever it is. Okay, now, because I've assumed that the input is an uncorrelated sequence, then this matrix phi transpose phi, for large amounts of data, becomes a diagonal matrix. And so when you look at the covariance of the estimates, it's just this diagonal matrix times the noise covariance. And it's very easy to see then for large n that the variance of each parameter estimate is given by this expression. It's a good time to ask, how many people in the audience know about this expression? Just put your hand up. Is this familiar? Okay, not that many, but maybe people aren't answering the question. Okay, so this is standard least squares estimation, the simplest kind of estimation. And let's have a look at this expression and see if we like it. What it says is that your errors, this is a measure of the mean square error in your impulse response estimate. And what it says is that the more noise you've got, the greater the errors. Oh, that's good. It also says that the larger the inputs you've got, the smaller the error. And the more data, this capital T was the amount of time you looked at the system. The more data you've got, the estimates get better and better and better. That's great news, isn't it? Oh, you collect data for a long time, you do a least squares fit, and you find the coefficients of the impulse response of the system with greater and greater accuracy. Fantastic. So what's the problem? Well, the problem is I'm not interested in the impulse response. I said I was interested in the frequency response. Now, the frequency response is a little bit different because in order to calculate the frequency response, what I have to do is to take the Fourier transform of the impulse response. Now, come on now. Now, this time I'm going to ask, who knows this fact, that the frequency response is the Fourier transform of the impulse response? Come on, put your hand up this time. Okay, so those who haven't got your hand up are either not understanding my poor English, because I also speak bad English, because I come from Australia, and we don't speak the Queen Elizabeth's English. We speak a sort of a funny dialect, but it's not as bad as those from the country just north of you. If you can't understand anything I say, don't hesitate to ask. Right. So we all know that the true frequency response is the Fourier transform of the impulse response, and so our estimate of the frequency response is the Fourier transform of our estimate of the impulse response. Too easy. But the problem is that all of the coefficients in the impulse response get used to calculate one frequency domain estimate, every one of them. Now, we found that the estimates got better and better of the impulse response as we collected more and more data. But the trouble is we're now using every one of those impulse responses. Now, if you don't believe it, just think of the DC gain. Come on, tell me what the DC gain is as a function of the impulse response. Somebody want to tell me? What's the DC gain as a function of the impulse response? I didn't hear the answer, but it's the sum of the impulse response, right? So if you sum up the impulse response, you get the steady state gain. Well, that's the zero value of the frequency response. Yep. But that means you have to add up every one of the impulse response estimates. So what does that mean? Well, that says that the more coefficients I put into the impulse response, the worse my estimate of the frequency response gets. So that's a bit of a conundrum, isn't it? Because we found that the impulse response got better and better. Every coefficient got better and better as I collected more data. But when I come to the frequency response, I have to combine all of my impulse response. And so now it depends on how many of these impulse response coefficients I have. So now we've got a different expression for the error, mean square error. And what is it? Now, just as before, it grows with the noise, it goes down with the size of the input, it goes down with how much data, but it goes up with how many taps we have on our impulse response. And so if you had a number of points on the impulse response that was similar to the amount of data you had, then your frequency response estimate is not worth anything. Right? So what's wrong? Well, we're trying to find the frequency response, but we're going through the mechanism of finding the impulse response. And if we make that impulse response too complex, then we have too many degrees of freedom in the model. And you can fit an elephant to anything, even things that aren't elephants. So, what's the solution? What's the solution? What would you suggest I do? The more coefficients, you would think, come on, if I use 1,000 coefficients in the impulse response, I get a better estimate, surely. But I've just said no. 1,000 coefficients in the impulse response gives you mean square errors which are 100 times worse than if I just use 10 coefficients. Right. Okay, so what are we going to do about this? Well, one idea that you might think of is to restrict the complexity of the solution. This is just motivation. All right. So, what we're going to do is to say, no, what about we restrict to just R coefficients in the impulse response? Just R. Now, we know that's not the real number. We look at the impulse response and it goes on for a very long time. But we've arbitrarily decided to just use R, the first R coefficients in the impulse response. Why on earth would you want to do that? Well, now you get two types of error. You get one error which is the error in the coefficients which you do estimate. But the rest of them are being set to 0. So if the other coefficients from R plus 1 to n are non-zero, then that gives you an error too. So you can see now we've got two errors. We've got one where the noise is causing errors, and one which is due to the fact that we've deliberately made the impulse response short. Deliberately. Okay. So now if you take the expected value squared of the previous expression, you now find that you have two errors. Now the first error is this one. This is the same one as we had before. This one grows with the size of the noise, it goes down with the size of the input. It goes down with the amount of data you collect, but it goes up with the number of coefficients that you decide to use in estimating the frequency response. Now what about this term? Well, this term is due to the fact that we deliberately didn't estimate some coefficients. Deliberately. Sounds pretty silly, but we deliberately didn't estimate some coefficients. So what we do is we call this error a variance error. It's the one due to noise. And we call this one a bias error because this one is due to the fact that we deliberately decided to use a low order model. Yep? So this is the bias variance problem in the simplest way I can describe it. Now all estimation theory is governed by a bias variance problem. If you read books on system identification, including my own, you'll see that they focus on variance errors. They talk about the impact of noise. But here I've introduced another error, which is the impact of the fact that you know that the model you're using is never a real description of the real world. Now, two errors, bias variance. And so if you're interested in fitting models to anything, robots, vibrations, nanomaterials, economic systems, anything else you like, then you will always have a bias variance error. Bias variance. Okay. Now what you've seen is, let me go back to the previous slide, what you see is that as I increase the model complexity, so the variance error gets bigger. So the more things you've got to find, the harder they are to find. Right? If I just tell you to find out one thing about me, it's really easy. I come from Australia and they were very nice to put the Australian flag up there in case I forget. Right? Yeah. At least they don't come from Scotland. They decided that they would stay in union with the British. And we are too. We have the Queen as our the Queen of Australia. Okay, so as you increase the model complexity, so the variance error grows. The more you try to find out about me, the more unlikely, the more likely you are to not get everything right. Where was I born? Does anybody know where I was born? Anybody? That's sad. Sydney. It's a reasonable guess, Sydney. Any other guesses? Where was I born? Sydney's not right, by the way. Any other guesses? Melbourne. This is a test on your geography of Australia. We've got Sydney, Melbourne. All right. No, Melbourne's not right. Another guess. Who knows another city in Australia?
Newcastle.
Ah. So Newcastle is where I come from now. No, I wasn't born in Newcastle. Adelaide is getting closer. That's warmer. Adelaide. Who's been to Adelaide? Put up your hand if you've been to Adelaide. Somebody's been to Adelaide. Great city, isn't it? Very quiet, nice city. City of churches, Adelaide. Sydney's nicer though, I think. Now, I was born in Broken Hill. Now, Broken Hill is a city way out in the desert in Australia. And it's exactly the same as the environment around here, only a lot drier. Right? So that's what Broken Hill's like. It's a mining town. And there was a company that was formed in Broken Hill. Does anybody know what that is? Come on, you know. Yeah, Broken Hill Billiton, Broken Hill originally, Broken Hill Proprietary Limited, made a fortune out of Broken Hill because they found the richest silver, lead and zinc ore body in the world. Right? And then they formed steel companies, and that's where Newcastle was a steel city before the steel industry went to China, as they all do. And but meanwhile, BHP Billiton have made a lot of money, and of course, BHP Billiton have mines here. Right? So the origin of the mines here are from the city where I was born. Right? Was actually the company was formed by a guy riding a horse around the boundary fence of the property that he worked on. He worked on a property called Mount Gibbs Station. Does anybody like history? Yeah, it's better than maths, isn't it? So you wait till you get my application, you're going to love it, honestly. Anyway, yeah, history's better than maths. So where was I? Oh yes, so this boundary rider was riding around the property. Now you've got to imagine that it's a lot drier than here. So the property is huge. Right? One single property is about the size of the United Kingdom, and he's riding around it on a horse because there's no rain. They have one sheep per 4 acres. Okay, so he's a boundary rider, and he stumbled across some rocks which he thought were tin. He was an amateur geologist. He thought they were tin. And he sent them off to Melbourne to be analysed, and it turned out to be silver. Right? Because silver doesn't look very fancy when it's in its ore state. It doesn't look very nice. But they told him that this silver body that he'd discovered was unbelievably rich in silver. And so he staked out a little piece of ground. And a little piece of ground was called Broken Hill Proprietary because it was on the top of a broken hill. So there you go, that's the origins of the company I work here. Okay, so this is the variance error. It grows with model complexity, and now you know where I was born even. Now, there's also a bias error where you deliberately make the model less complex than it should be. Okay. Now, let's just make a guess. We know that the variance error goes up proportional to the number of coefficients we use. What about we assume that the bias error gets better as we increase our model complexity? Bias error just says, does there a model even exist that matches the system? And of course that gets more and more likely as you add more and more coefficients. So if we assume that the variance error, we know the variance error is growing with the number of coefficients, let's assume that the bias error goes down 1 over the number of coefficients. then you can work out what the optimal complexity model is. Add these two together, differentiate with respect to R, set the result to 0, and what do you find? You find that there's an optimal model complexity, which has nothing to do with the true model complexity. Well, it has something to do with it. But it's a trade-off between bias and variance. And so that's the message in this talk. Bias versus variance is everything. And the right model order is never the true model order. It's always one that's a little bit more restrictive, because that helps you with bias versus variance errors. Okay, and amazingly, it brings bias error equal to variance errors, which says if you've got a whole bag of errors to deal with, you should try to make them all equal. Don't spend your life trying to make one error really small if there's another error that's really big. I call this homogeneity of errors. There's no point wasting your time on one little thing if there's something else that's this big. The right thing to do is try and make all errors the same. Okay, so what's the conclusion? It's not always best to use the true model. Artificially restricting a model complexity can be helpful, and it's all about achieving a good compromise between bias and variance. Who's heard of the Kalman filter? Come on, I'm asking all the questions. I want somebody else to ask a question. Somebody's got to ask a question. The question you could ask is, what's this got to do with Kalman filtering? Come on. Who's going to ask it? Excellent. That's a very good question. What's this got to do with Kalman filtering? Well, the Kalman filter is an estimator. All right? And if you estimate the states using a Kalman filter, you get a bias variance error. You didn't know that. Maybe you did. There's a bias variance error. And you might think it's okay to use a huge model. But sometimes it isn't, because a huge model is going to introduce state error, estimation errors. And then when you come to use those states to design a controller, you might be in trouble. The Kalman filter is more clever. Kalman filter does regularization. And how does the Kalman filter do regularization? Because it hypothesizes process noise. And process noise says something like, look, the model is not quite exact. I've got this model, but it's got a bit of errors on it. And so Q versus R, if they're the terms you use here, Q versus R, Q being the process noise variance and R being the measurement noise variance, that gives you a handle on bias versus variance. But there are other ways of getting a handle on bias versus variance, as I'm going to show you. Right? But Q in the Kalman filter is a bias variance, and in fact that's an example of L2 regularization. Right, so we've been through the first bit. We've seen that as model complexity goes up, variance errors tend to go up, but bias errors tend to go down. Right, so now I want to introduce you to tools. And now these tools come from statistics. The first part of this is about statistics. The second part of the talk is about optimization. I'm talking about statistics for the moment. So, tools. Now there's a whole lot of things here. Don't worry, it's not examinable. But don't panic either, because these are just names. And when I first heard these names, I panicked. Ridge regression, lasso. That sounds like the boundary rider in Broken Hill going around the fence. Lasso, you know, lasso. Group lasso, I nearly said group lasso. Group lasso, elastic net, etc. But these are simple things. Okay, so start at the bottom of this slide, which is here. If you're doing maximum likelihood is a very general tool for estimation. What it says is you form the probability distribution for the data and you parameterize by a vector of parameters theta. And maximum likelihood just says, you give me some data and what I'll do is return to you that value of theta which maximizes this thing called the likelihood function, which is just the probability of the data given theta. Least squares can be thought of as maximum likelihood under a Gaussian assumption. Okay, so, but I've just shown you that least squares can be problematic. Can be, not always. And so what you can do is to put a term, an extra term, that says some values of theta I don't like. So you have a sort of penalty term. Yep? Right, so you do maximum likelihood, but you add a penalty on certain values of theta. Now, one thing that happens if you overfit data is that you get usually get very big estimates of the parameters. They're ridiculous values. Okay, so one way to regularise is just to say, look, I don't like big values. Big values contribute to this. Please don't give me a big value. And that's a regularisation. Okay, so how can we motivate in a different way this g theta? I seem to be, come on, I want some questions. I seem to be asking you questions. Who's heard of Bayes' rule? Some people have not heard of Bayes' rule. Reverend Bayes. Bayes' rule. Bayes' rule is a way of injecting some prior knowledge about the things you're estimating. And what Bayes' rule says is that the probability of theta given y, which is the likelihood function, can be written as... There's something wrong with this, isn't there? This actually is, I apologise, this is py given theta. Is p theta given y multiplied by p theta divided by py. And what this means is if you take the log of this, what you do is you have that the a posteriori distribution of p theta given y, actually this is py given theta, is log py given theta plus log p theta. This is just a normalisation which is unimportant. I apologise for this mistake. This is py given theta. I looked at these slides many times and I didn't see it. Isn't that true? How many times, when you look at something with an arrow in it, you always read what you want to read.
They say that when you correct something, you introduce some other error.
Yes.
It's a less important one, but you always introduce a new error.
That's true. So the suggestion was that every time you correct something, you introduce one more error. Actually, in my experience, if I correct one thing, I introduce two errors. I have a funny story about that. I was writing a book with a guy called Sang Sin. I wrote this book, Goodwin and Sin. Now, what was interesting about Goodwin and Sin? I think it was an okay book, but because it was written with a Chinese co-author, it became very well known in China. At any rate, I was writing this book and I wanted to demonstrate to the poor lady who was typing this fact that there's always errors. So to order to illustrate, I said, look, if you just turn to an arbitrary page and point to somewhere on the page, there's likely to be an error. Oh, there is. So I pointed at some arbitrary point and there's a mistake. There you go. I fixed that one. Yeah. Okay, so what we've seen is that the maximum a posteriori estimate can be written as a problem of maximising the likelihood function, but with the logarithm of the prior distribution of parameters added. And so if you interpret this as g theta, then you've seen that you've got a Bayesian interpretation of regularisation. Right? So let me take you back to where I introduced regularisation. I said do maximum likelihood but penalise some values of theta that you don't like. And what we've found over here, is that you can also think of this penalisation as the logarithm of the prior probability of those values of theta that you like. Too easy. Right, now if you make different assumptions on the prior distribution of theta, you now get this smorgasbord of techniques. Okay, so what's ridge regression? Ridge regression just says assume a Gaussian distribution for the errors. And that's what the Kalman filter does. So the Kalman filter is an example of ridge regression. And all that ridge regression, when you take the logarithm of the Gaussian distribution, you simply get some term, the square of the parameters. So all that ridge regression is doing is penalising the square of the errors. So you don't use very big values, because very big values means that this term would be big. So that's ridge regression. You put a quadratic term. Right. What about lasso? Who's heard of lasso? Come on, I have. Anybody else heard of lasso? 1, 2. Anybody else heard of lasso? 3. Come on, be honest. Don't put your hand up again. Is there anybody else heard of lasso? 1, 2, 3. Only 3. You know, that's good. Why is it good? Because then I can tell you something you haven't heard of before. Lasso is a really important strategy, and it's very frequently used in modern estimation. And what's lasso? Lasso says that you use this funny prior distribution, and you'll see that it adds up the magnitude, not the square, but the magnitude of the parameters. Magnitude of the parameters. And so what does that mean? Well, that says that you're doing an L1. We call that L1 normal regularization. And this is called lasso. So if you're working on machine learning and you see lasso, you'll know now that they're just adding to the maximum likelihood and a correction to say, I don't like big values of parameters, and by the way, I am going to, when I say big, I mean their magnitude, not their magnitude squared. That's lasso. Well, now we can go a bit faster. What about group lasso? Group lasso is just using the magnitude, but you scale them differently for different parameters in different boxes. So if you take your parameters and put them into 5 boxes, you can use a different regularization in each box. Every time it's the magnitude, but this might be 3 times the magnitude, this one 5 times, this one twice. That's called group lasso. Right, group lasso. Then you get elastic net. Elastic net is what I wear when I go swimming so that I don't perturb my hair. Works too, doesn't it? You can see my hair is perfectly in place. It's elastic net. But actually elastic net is just a fancy word for a normalisation which combines L1 and L2 regularisation. Now, which regularisation do you want to use? I've convinced you, I think, that regularisation is a good thing because it says somehow I don't want to estimate everything under the sun. Restrict for me, please. And that's what regularisation is all about. But which one? Well, if you're a Bayesianist, then the regularisation comes from your prior knowledge. I don't like those values, I like these ones. Don't estimate if the parameters are too big, and by too big I mean that their square size is too big. So that's Bayesian, but sometimes it comes from just the heart. That you're really worried about having too many parameters. Now, one really interesting one, which is the purpose of all this talk, is what's this zero norm. Now, the zero norm doesn't exist. It's not a norm. What does the zero norm try to do? It counts the number of parameters in the model. So if you were to say, I want to do a Kalman filter, but I want to only use 3 states. I don't know which 3 are good. I've got a 1,000-state model. I'd like to use 3 states, but I don't know which 3. So what you would say is, why don't I minimise the normal least squares type thing that the Kalman filter does subject to 3 states, but I don't know which 3. Now, why isn't that a sensible question? Come on, help me. Why isn't just saying, I've got a 1,000-state model and I want to just have 3 states, but I don't know which 3? Why is that hard?
Numerically, it's strange, right? Because
Yeah.
you make a big difference between being 0 and 10 to minus 6.
That's right. One problem is that it's numerically strange because you have this black and white thing. I need to have 3 states, not 4. 3. That's one issue. But another issue is that this is a combinatorial problem. How would you do it? How would you work out what's best? One thing you could do is to say, how many choices are there for the first state? Come on, you can all answer this. I've got 1,000 states. How many choices are to choose the first state? Hey, that's pretty good. Whoever said that can stay back and clean the blackboard. Right, there's 1,000 ways of choosing the first state. How many ways are there of choosing the second state? That's right, there's 999. And how many ways are there of choosing the third state? 998. How many models do I have to study in order to work out the best 3 to choose from 1,000? 1,000 by 998 by 999, which is approximately 10 to the 9 models. 10 to the 9. 10 to the 9. How many atoms in the known universe? Ooh. Anybody know? How many atoms in the known universe? Yes? Okay, you can very easily get up to problems where you encounter how many atoms in the known universe. The answer is about 10 to the 70. So if you start doing these combinatorial problems, you'll soon be running as many Kalman filters as there are atoms in the known universe. So this is not a good idea. Right, so this is not good. So why do people use lasso? If you learn nothing else from my lectures other than the story of Broken Hill Proprietary Limited, the boundary writer's name, by the way, was Charles Rasp. It's a history lesson. But the lasso idea comes from this wonderful observation. And the observation is that you might like to use the L0 one, which says count the parameters. Now let's count the parameters. If I'm on the axis, my count is 1. If I'm sitting in this region here, how many parameters am I using? 2. So the L0 regularization, which you never want to use because it's combinatorics, is 1 here and 2 here, 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 and here. Fine. What about the L to the half regularization? We can see that looks a little bit like this, but it's just sort of a bit more smooth, and you get 1 on all this curve, and you get less than 1 in here and bigger than 1 out here. You can see it's something like this, but instead of jumping from 1 to 2, it's got this boundary where you're 1, and it's less than 1 and greater than 1. What about the L1? Well, the L1 straightens it up a bit more, and it's 1 on this boundary, and it's less than 1 in here, and it's greater than 1 out here. And what about L2? Well, it's just a circle. Now, here's the wonderful theorem, that if you use this, you often get this answer. And there are conditions under which, optimizing with this regularization, you get that answer. And this is amazing. Why would you want to use this rather than that? Because this leads to convex optimization. Another thing I can tell you, if you didn't already know, that, what am I going to tell you? Yes, that convexity is everything in optimization. Nonlinearities mean nothing. Size of the problem means nothing. I've solved problems with 1 million variables. 1 million. Doesn't matter. As long as it's roughly convex, it's a breeze. As soon as it becomes non-convex, it's impossible. So the big divide is between convex and non-convex. And so this is non-convex, and this is non-convex. This is the first one that's convex. And so using this one gives you, means that you can use standard software and it converges like a breeze. And so if ever, I think there are only 3 people who said they'd heard of Lasso. But if somebody says to you, I want to estimate a model of restricted complexity and I'm really interested in having a small number of parameters, 5 parameters or 5 states, then think of Lasso, right? Because although it's not this, there's a theorem that says that using this quite often gives you the solution you would get from the non-convex one. So it's a convex relaxation of the problem, which works magically because it often gives the right answer. Yep. Okay. Now there's other ways of putting this all together, which is variance Gaussian mixtures. This is another big technique in statistics, and what they do is they form prior distributions by mixing together other simpler distributions. They call these things variance Gaussian mixtures. And what they do is they form the prior probability by convolving a probability of a parameter given another parameter and the probability distribution for that other parameter. So you can keep building these things. And let me just show you very quickly. If you use these 2 distributions, so you use two normal distributions and you convolve them in the right way, you end up with the Lasso regularization. So these variance Gaussian mixtures are very popular in statistics, machine learning, etc., because they allow you to produce rather complicated prior distributions. Okay. So I want to finish this little first bit with the expectation maximization algorithm. Who's heard of expectation maximization? Come on, don't disappoint me. 1, 2, 3, 4. Wow, 5. And the rest of you haven't. Is that true? Expectation maximization. Okay. This is really something you can take home. I don't care what problem you're working on. I love expectation maximization. Right? Because often it allows you to take a very complicated problem and turn it into a complicated problem. Not bad. It's a way of dealing with some very complicated estimation problems, and I want to tell you about it. Yeah, okay. So what's the idea? What's the EM algorithm? Let's assume that if you could measure this, we're going to divide the measurements into 2 classes. There's things I can measure and things I would like to measure. Who knows about state space models? Good grief, come on, please, everybody, come on. Come on. State space models. Everybody knows about state space models. Problem with parameter estimation with state space models is that you only measure the output and not the states. If only you measured all the states, it's easy. Even a guy from Broken Hill in Australia could do it. If you were to measure the states, it becomes trivial to do model estimation on state space models. But the trouble is, you only measure the output. Come on, x dot equals ax plus bu, y equals c of x. You only have y equals c of x. Yes? Right. And not having the states is bad. So why don't we do the following trick? Why don't we say, declare those missing states as hidden variables and use the EM algorithm? Because the EM algorithm is a wondrous little trick invented by a statistician called Dempster. And what it does is it allows you to do a little iteration which basically says, first step, estimate the states. Second step, estimate the parameters as if I knew the states. Third step, estimate the states. right? And go round and round. And this converges to a local maximum of the true likelihood function if I didn't give you the states. Magic stuff. Magic stuff. Okay, you either know it or you don't. And in 10 minutes I can't give you the proof. I didn't get a chance beforehand to ask this, but you can get a copy of everything I'm saying, either in hard copy form, I'll leave somewhere a photocopy of all the slides, or I leave a disc with the whole presentation on it. All right, so what do? It's basically what I've said. You basically declare, these are the hidden variables, they're the things I would like to measure but I don't, and here's the things I do measure, and you go round and round, you say estimate the parameters, and then how do you, say in a state space, if I give you the parameters, a parameter estimate, how do I estimate the states? Come on, you're given the parameters, an estimate of the parameters, and you're given the output, and I need to estimate the states. What would you use? I've given the parameters, I give you the output. How do you estimate the states? There's a famous person's name. Kalman. That's right. So the first step is, given a parameter estimate, estimate the states. That's Kalman filtering. Now I've got an estimate of the states. Now estimate the parameters as if I knew the states. Now it's not, and it works. It works fantastically. And there's software available to do that. And if you ever need to fit a state-space model to something, it's a great way of doing it. It's not the only way, but it's a great way of doing it. Okay, so now I've given a proof that the EM algorithm, why it works. A picture's worth 1,000 words. I'll try to give you the picture, but I've given you a little proof. If you collect the notes, you get the proof. And how does it work? Well, the function you actually maximise is not the true likelihood function, but it lies underneath it. So if you, in one step you go here, you can see that you've gone uphill on the likelihood function. And then if you go from here uphill, if you go to the top of this function, you can see you've gone even higher on the likelihood function. So you go round and round this loop and you maximise this difficult likelihood function. So that's the EM algorithm. And the proof's given in the slides. And if you want to learn a little bit of statistics, if you want to revise your knowledge of Bayes' rule, I was surprised how many people didn't know about Bayes' rule. I think you were kidding me. You must have heard of Bayes. But if you want to revise your knowledge of Bayes' rule, then go through the proof of that the EM algorithm works. Because there's just a few little expectations and you'll find that it works. Right, so let me then give you a little application of this. And again, so here we're going to fit to a real system of high complexity, but we've decided that we're going to fit a low order model and we're going to have some model errors. This tricky problem. Now we're also going to put these model errors, we're not going to try and estimate those. If we're going to estimate the model errors, we're back to estimating the model. So what we're going to do is instead to declare these model errors as hidden variables. If I told you the model errors, it's trivial, you then estimate the simplified model. And then if I give you the simplified model, you could tell me something about the model errors. How would you do that? Expectation maximisation. So that's what I'm going to do. I'm going to have just two parameters. This is just for illustration. Two parameters in my simplified model, a couple of parameters in my model error. But I'm not going to try and find eta naught and eta 1. I'm simply going to try and find their distribution. So I'm going to estimate the prior distribution on the model errors. It's all tricky stuff. So there's a regularisation that's parameterised by two parameters. Let me jump to the pictures. Don't worry about all this. This is details of the EM algorithm. But if you haven't heard of the EM algorithm, then you won't follow this. But when you get home, if you want to read this, then you'll find this is easy. It's really easy. The wonderful thing about the EM algorithm, it takes a difficult problem and turns it into two simple problems which you solve recursively. Basically, you find theta, the simple model, and then you look at the distribution of the residuals, and then you look at the parameters, look at the distribution of the residuals. You go round and round that little loop, and you find out that you found everything you wanted to know. Magic stuff. Okay, so here, they're the details of the EM algorithm, and here's a little application of it. This is a set of systems, so every time I look at this system, it has a different frequency response. So think of an aircraft flying through different atmospheric conditions, the model changes. Think of a robot performing a task, and it picks up different masses. And when we pick up a different mass, the dynamics change. But we don't know the mass it's picked up, and we're not so interested in that. We want to get some global model. So we treat the masses as under modelling. You can use this tool. Okay, and why is this a good idea? These are the true parameters. These are the estimates obtained by the expectation maximisation, and you can see that the answers are very good. And if you I don't know if you've heard of prediction error methods, but they sort of fail completely because I've deliberately chosen a problem with a lot of modelling errors. And prediction error methods don't count for modelling errors. Okay, so that's the story. And this is the convergence of EM. You can see it very quickly finds the right values. Right, so what's the summary? I'm going to give you a little pause in 1 minute. It's 1 hour, so it's a good time to have a little break. Then you can ask me some questions. But I've talked about to be careful about overfitting. You can fit an elephant to anything. Yep. I don't try to fit overcomplicated models. They will fit the data perfectly, but they're useless for prediction. Right? It's a well-known problem in machine learning that you can learn by looking at data and you think you've got a wonderful model because you fitted everything perfectly, but then when you come to predict the next data point, it doesn't work. Right? Overfitting. That's what I've talked about, and I've talked about that that as you increase model complexity, so in principle the model gets better, but the difficulties of estimating the model get harder, which says bias errors go down, variance errors go up. And I've talked about tools for dealing with this, which are fancy statistical terms: lasso, ridge regression, group lasso, elastic nets, etc. And I've given you a simple example. Now what I've done also, if you're interested in anything I've said, if you're not interested, that's all right. If you are interested, then I suggest you try to read the references. And all I've done, in 1 hour I can't tell you everything. Right? But these are the right references to follow up and understand it. Right? I'll give you references and then even more references. And if this were a course, I'd say that the material in this paper is examinable, which would really make it hard, wouldn't it? Okay, and then there's the proof of expectation maximisation if you want to look it up. And I'm not going to go through that. You see it's got a lot of expectations and logs and stuff in it. Okay, it's time to have a rest of one form or another. I suggest that everybody stand up at least, right? Turn around and sit down. And if you want to go to the bathroom or sing a song or whatever. So, 5 minutes break, come on. No.
TEM methods also assume a prior knowledge of the system.